you have to trigger the effect of the fault. Somehow, some signals have to go to the site of the fault and create a situation which would be opposite to the effect of the fault, and it's called fault excitation. And then we are going to need error propagation. So, once a fault has been excited, you will create an error, and in order to test for that fault, somehow you have to propagate the error to the output so that you can observe the error. And now let's look at some notation. We are going to indicate normal function by f and faulty function f alpha, where alpha is the fault. Okay, let's come here. Now we define, this is a definition, a vector now you might have noticed that vectors in a printed book are often indicated by a bold character, so it looks darker, but that is too hard if I'm writing on the board, so sometimes I will do this to indicate that that is a vector. Is a test if the normal function for the vector is not equal to the faulty function. Do you all agree with this? So something is a test if the normal function and the faulty function, they have different outputs. Okay, you all agree with this? Okay, so this is simple. And now let us state it differently. All the tests are included in this expression, which is given by now remember the definition of exclusive OR. For an exclusive OR, the output is 1 only when the two inputs are different, right? So for all combinations for which normal function and the faulty function are different, those combinations are tests. So all the tests are included in this here. And this is a rather interesting expression. And okay, let's illustrate this. Let us say here we have the circuit A, B, and here's the output. And let's assume that this is a fault, and let's assume this is a stuck at one fault. So what is the normal function? And as you know, the normal function is f equal to ab bar. This is a NAND gate. In other words, in a Carnot map, we have, this is a NAND gate, right? Okay, what about the faulty function? What is the faulty function? This is stuck at 1, it's always 1. So output is equal to nothing but B bar, right? So a Carnot map sorry about that. Let me be consistent here. Okay, B bar. Where's B bar in this Carnot map? This is B bar. Notice there are 4 possible combinations. For these combinations, the normal function has output 1. 4 possible combinations. For these combinations, the faulty circuit has output 1. So question is, which combinations are the tests? The combinations for which F and F alpha are different, right? So where are they different? So same here, same, and this is where they are different, right? So the test is, and in fact you could do that, F exclusive or F alpha would be this. And thus T, which is equal to A bar V, which we can also write as 0, 1, is a test, is the only test. There is a test, and there's only one test in this case, which is 0, 1. And you can easily see, here 0, here is 1, the normal output. In this case, what is the normal output? This is 0, so this is 0, so this is 1. And if it is stuck at 1, this is 1, this is 1, this is 1, so this is 0. So you can see that this is a test, because the normal and faulty outputs are different. Any questions on this? Notice here that I got this F exclusive or F alpha visually using Carnot map, but if you prefer to do it algebraically, you can take an algebra, you can take AB bar exclusive OR with B bar, and there you will get this E bar B. Either way, you will get the same thing. I usually like things visual because that way it's easy to see what is that I'm doing. But some people prefer to do it more algebraically. So that's a thing of personal preference. One advantage I think with visual is that you can spot any errors easily. So you can kind of see what you are doing. Okay, that brings us to the first formal method for test generation using Boolean algebra. and it is called the Boolean difference method. And in somebody took away that clock. I was thinking that maybe I should get some batteries for that clock. So maybe I have just to rely on my watch. And here is a theorem. Let me state first the main idea using a theorem, and then I will prove the theorem. And let's assume that an input x sub I has a fault alpha, which is stuck at 0, then the set of tests are given by x sub I multiplied by df by dxi. Now this is the Boolean difference. It looks like ordinary derivative, but it is not an ordinary derivative because, of course, everything is Boolean here. So where df by dxi, the Boolean derivative, is defined as the idea is actually simpler than the expression if you think about it. So basically, where df by dxi is defined as the normal function, and the same thing with x sub I replaced by its complement. Now notice that one of them has to be 1 and other has to be 0, right? So you can also write it this way. Where this is defined as this, or this is the same thing. So here's the theorem. Now the theorem says that if input x sub I is stuck at 0, then all possible tests that exist for that fault are given by this expression, t, where t is given by x sub I multiplied by df by dxi, where df by dxi is equal to this. Notice that the meaning of this is, so this is a set of conditions for which f is sensitive with respect to x sub I. This is what we mean. So a set of all conditions for which